they will then consume this energy. So it's all about generation of energy, the transportation of energy, the distribution, in other words, and the transmission, and then in the end, the consumption of that energy. So you can decide where you want to operate. Now, lately, we've been focusing on solar farms and alternative energy sources. These all tap into the electrical grid that we've created across our country. And this electrical grid is maintained and managed by Eskom. It is part of their responsibility and their mandate, and they make some money out of that. When, also of late, we've been looking into power and smart grids. So smart grids are typically smaller grids that are managed locally, and the grid itself is not smart, but it's stacked with smart technology. So we measure and control the flow of energy in a very, very intelligent way. And that makes up a smart grid. So just remember the three main portions of a network or an electrical network. It's the generation, the distribution, and the consumption of electrical energy. Now, where does the electronic engineer fit in? Well, all of these plants have control systems. And the control systems are typically linked to supervisory control and data acquisition systems called SCADA systems. And these systems control and give information to managers on how to control the generation of energy. They measure the distribution of energy, the metering of, because we have to, we have to measure the consumption and we have to bill according to that consumption. So all these aspects are typically done by electronic engineers. So our electrical and electronic engineering degree covers both of these disciplines to a larger and a lesser extent, but they do overlap. For example, an electrical engineer might be doing control systems, and some electronic engineers might actually venture into the high voltage spaces as well. And you will see that there are DC and AC grids. That stands for alternative current and direct current. And both these currents are currently being used all over the world. These types of energy are used all over the world. And you will also notice that the solar farms and the wind farms of late have become very popular. And the solar panels specifically have become part of architecture. So they are being designed into homes and larger buildings as part of the actual building. So yes, solar energy is here to stay. And if you want to venture into that part of energy generation, you will definitely have your job cut out over the next 10 to 50 years, I believe. Also in the nuclear facilities, we do have the mechanical engineers also focus on nuclear facilities. But again, it's also part of an electrical engineer's job to take that energy and to distribute that energy across the country. Right, so let's go into the next one, electronic and computer engineering. Now, this is more our direct field of application. But I must say, you must remember, when you become an engineer, you won't be just one of these engineers in your life. You'll stray a bit, and you'll become a product development engineer, or you might be focusing more on the industrial aspects of engineering and so on. So you're never bound into just one discipline. You will always, over time, you will develop and you'll become a manager, and you'll become a project manager, a systems engineer, and you might have different job titles as you become more mature and more experienced. But let's talk about electronic and computer engineering. Well, there's lots of AI. I'd like to refer to the lots of AI because that sounds very exciting, and the big data to the left. But let's see what happens in electronic and computer engineering. We also have processes that generate information, and this is what we do in electronic and computer engineering. Is we generate information. This is done by means of sensors and other sources of information. It could be activities in the field that we're monitoring, things that people do, like vehicles that travel and so on, and we measure their location. It could be different sources of information. That information is then also transported, and that you'll see the similarities between electronic and computer engineering and electrical engineering in the process that is followed. So information is either generated and processed, it's distributed, and it's consumed. It might be consumed by a data center and users of a data center, and this is an example of a data center to the right here. And this is a SAP data center. And I can't remember where it's situated, but it's a SAP data center. And at the bottom, just for the fun of it, I included the Google development offices, just so you can see that it's lots of fun to be a software developer as well. But the data center is to the right. Now, so the larger banks, you can imagine that the larger banks will use a data center and all your information will be stored in the data center. It'll be accessed by users. So I'm going to follow the path going back again. We might then also generate information from the data center. We'll distribute it then back to the clients where it's again consumed. So there are two paths. It's an upward path towards the data center or the big data, and then the downward path where the consumers sit on the left-hand side. So what do electronic and computer engineers then do? Well, we have to create the network, the communications network that'll transport the information. So that's typically done by telecommunications and IT network engineers. We'll have lots of devices in the field, and this could be a farm, this could be an industry, it could be any operation where a lot of information is generated. And we would then send that information to a central location across this network that we've created. We'll do lots of processing, and that is where AWS, so it's Amazon Web Services, and all the larger data center owners will then provide you with virtual machines that you can rent from them, and you can run your software on them. Then when we've processed that information and we've stored it and we make it available in a different form, we'll send that information or in a processed form or new information back to the operational site where people will be using it, or we might have IoT devices or other intelligent devices that will be using some of that information again. So the creation of these intelligent devices is also the job of an electronic and computer engineer, because many of these devices have embedded systems in them, which means it's a smaller form of computer, and the embedded computer will then take that information and do something productive with that. Now, you can imagine your phone is one of those devices. You generate information, you send it into the cloud via WhatsApp, and even what we're doing today, the screens that the video that you see in front of you, that was generated on site. It's then sent to the Zoom server. It's then sent back to where it's processed, and it's sent back to all the other people listening, for example, to the Zoom session now. Now, what is big data? So big data is exactly what it says. It's not data that's big, it's lots of data together, and we would like to gain some insight into that data. Now, this data can tell us more about what people do and how they think, and how we can use that information to make intelligent decisions. And that's where the lots of AI comes in at the top. We extract patterns and anomalies, things that should happen and shouldn't happen. We identify them, and then we make decisions based on what we see. So, for example, this could be a security system where we see people doing things that they should be doing and we're comfortable with that. So we'll leave it at that. But then when we see people doing things that they shouldn't be doing, then we would like to make intelligent decisions and then take action in this operation. So this could be a control center where lots of information is passed up passed up to the stream at the top here. It's generated by people doing things. It could be a criminal attacking a bank, for example. We send that information to a control room. The control room makes intelligent decisions, and then it sends back instructions to a reaction force that will then do something on site. And we would like to automate much of this, and that is why we use lots of AI. So that is basically what an electronic and computer engineer does. So you can imagine that if we measure electrical networks at the bottom here, and we send that information to Eskom's central location, and they take intelligent decisions, then they can send repair technicians, or they can send bills, they can send different things to the operational sites, And that is where electronic and computer engineers overlap with electrical engineers, for example. So I'm sure that this gives you an idea of what computer and electronic engineers do. You can imagine that computer engineers write lots of software, whereas electronic engineers will be focusing more on the devices and what we call lower level software. It's the software that runs on smaller devices. And then the larger devices, the larger software systems are mostly running on in the cloud, which is this area on the right-hand side. The cloud is simply a combination of software systems that run on this data center. So if when you speak to something in the cloud, it's actually hosted on quite a number of these data centers to the right, and all these data centers then provide that service to the end users who are sitting elsewhere. All right, so that is something hosted in the cloud. Software packages such as when you look at MS Word and you use MS Word online, that the Office products, they are hosted in a data center. So let's have a look at mechatronic engineering. Now, this is an interesting one because it is not one discipline. It's actually quite a number of disciplines combined. And I've stolen this little picture here from MIT, and what it says is and I believe it's MIT. But anyway, so what it says is mechatronics sits in the middle, and it's made up of control systems, electronic systems, mechanical systems, and computers, and all these things together produce mechatronics. Now, okay, so what does a mechatronic engineer do? What do they actually build, and what would the life of a mechatronic engineer be? From day end to from day start to day end. All right, so at the top, I've said that there's measurement and control. So what is measurement and control? Well, that's a little algorithm that runs that measures things, and it makes decisions on how close to a target value the measurements are. And if that measurement is close to a target value, we're happy. If it's not, then we adjust the system to act closer, to give us an output or a result closer to that target value. This is very much like if you study for a 75 mark and you get 80, you tone down so that you can get 75. And I'm just joking now, but you should obviously go for 90 and see if you can reach that. But if you study for 75 and you get a 90 mark, you've overstudied. If you study for 75 and you get a 50 mark, well, you've understudied. Then you need to adjust, and that is an example of a control system. So you get what you aim for. And mechatronics, that's a very important principle because control systems form an integral part of mechatronic engineering. There's also lots of AI, and I'll get back to that a little bit later. On the right-hand side, you'll see robotics and automation. So where are these measurement and control systems used? They're used in robotics and automation. Now, we automate by setting the goals and implementing the control algorithms. That means that we can stand aside. We can set the system to measure what is actually happening, to look at the target values, and then decide what to do based on the algorithm to correct the system's behavior to meet the target values. And that's automation. And robots act in that way. We can program robots to build cars. We can program robots to assist people. You can imagine the number of applications where robots are sensible to use. There are some applications where robots are not sensible to use, and that's typically when you work with people. So there will always be a job for people. Don't be afraid, the robots won't take over. Mechanical interfaces, they are always there. We create mechanical interfaces between electronics and between mechanical devices such as vehicles. And I've shown at the bottom there, and Prof. Lienta, that this is part of her passion, is biomedical, the biomedical side of things. You'll see that we won't be measuring brain waves and we won't be steering space shuttles based on brain waves. That's not what we're going to do. It's a more practical side of things. If you look at a pacemaker of someone to to adjust the rhythm of someone's heart, that is actually a mechatronic device, and that's an interface. It could be a mechatronic device combined, and what I'm saying is that your heart is actually the mechanical, the biomechanical, or let's call it the biological part of the mechanics, and we interface with your heart with a pacemaker. But in the same way, we can interface with a vehicle's heart, which is the machine, and the ECU, the engine, the engine management unit, the EMU, or the engine control unit of a vehicle. And that is an electromechanical interface, or a mechatronic interface, if you like. And that is also part of the mechatronic engineer's work, is to build that interface to a vehicle, for example. Now we can track the vehicle. We know what the vehicle's performance is, just as we're looking at a person's heart using a pacemaker. We can understand what that person does. There are more practical applications of biomedical devices, such as when we're doing a sports, we put a device, we attach a device onto a rugby player's back, or whoever's doing some form of athletics or biokinetic movement, and then we can measure what that individual does and how that person is either performing in a sports environment, or even for rehabilitation purposes. We can measure and control what someone does. All right, so the vehicle is a good example, because everybody drives a vehicle. There are lots of little motors inside a vehicle, and when you adjust your rear view mirrors in the vehicle, you'll be using something developed by a mechatronic engineer. It's a little motor that interfaces with a mirror itself, and then when we push a button, we read the position of the button, and we convert that into something, into an action that moves the mirror into the direction that we want to move in. And that is an example of a mechatronic engineer's job. And that is a very basic one. And I believe in some vehicles, there are up to 200 little motors that have to be controlled. You can imagine how complex that becomes. Um, Adjusting the performance of the vehicle, that is a mechatronic engineer's job as well. And they use computing and processing, which I'm showing on the left-hand side, and computer-aided design tools in order to design the systems that actually do the work. So these computing and processing devices will make use of computer and electronic engineering principles. That's why it's called mechatronic engineering. But it'll interface, as I've said, to mechanical interfaces, and typically CAD systems are used to design those interfaces, and it'll design the devices that'll actually interface between the computing and processing systems and the mechanical systems. You can imagine the number of applications where mechatronic engineers will be a part of the design team, the maintenance team, the upgrade team. They will be part of the full life cycle of a system from the beginning to end, because of their wide range of skills. Now, I'm just returning to the lots of AI on the top. Now, the behavior of vehicles and the behavior of people and the mechanical movement of things follow certain paths in space. Um, and we need to measure these paths, and we need to optimize these paths. And that is why we use AI. We can measure the typical behavior of things, model that, and then control using the measurement and control systems, also using artificial intelligence. So we can either manually do it, we can program devices to do it according to a set of rules, or we can make systems that are adaptive. And that is what we call machine learning systems. And typically in a robot that learns to walk, and that's why I've put these two, the robotics and the mechanical interface at the bottom. Yeah, I put them on top of each other, because the lots of AI will actually teach a robot to act based on learning from experience. So that's in brief what a mechatronic engineer does. There are lots of other applications you can just imagine. Um, and Yeah, Lienta, I think Prof. Lienta, you've been part of the mechanical interface at the bottom here. You've built prosthetic devices. You've built clever things that work, that interface between mechanical, um, like a hand. I believe you've built a biomechanical hand, and all very interesting things that you can talk more about. And the future really is smart materials, AI, and lots of overlap between different engineering disciplines. So don't be blinded by the fact that there is a discipline. Some of these disciplines will overlap. You will work with material sciences people, you will work with mechanical people, you will work with lots of different clever people. And you yourselves being very clever, you'll be able to adjust and adapt just like the AI systems do. And that's in short what the three disciplines involve and entail. If you have any questions, you're more than welcome to ask.
Okay, I see there's one question so long asking us whether or not there's a difference between electrical and electronic engineers. So, and remember, you can ask questions. So please ask your questions.
Yes, please do. Yeah, an electrical engineer works with higher current and the distribution of electrical energy and the application thereof, whereas an electronic engineer will work with lower currents and lower voltages, and typically with the generation of information that we transport. So information will be transported and distributed as opposed to electrical energy that is generated and transported. And that's in short what the difference would be.
Okay, I don't see any other questions right now. So I think let's give Anna Maria an opportunity, and I'm sure the questions will start rolling soon.
Thank you, Lisa. Hi, everyone. My name is Anna Maria. So I would like to start today by asking you to imagine a world where you go on the internet and you order a pair of shoes. So let's say today we're going to order some tackies, and you find the color you love, and you tweak the design a bit, and then you press order, and the material is delivered to your home, and you print that on your 3D printer by yourself. And that is really a world that we know might be coming. It's something that we see coming, and we might not know who's going to do what. So we immediately ask what will need power. So that's where the electrical engineers come in. We'll need mechanical aspects of it. There'll be electronic aspects of it. But the truth is, what we do know is that an engineer will be involved there. So if you choose engineering, it really is always an exciting field, if it's now or in 20 years or 10 years back. And I just want to thank Lieta. Thank you for allowing me to share my story today, just to show the ladies what an exciting world we live in as engineers. As you see, she's also very accomplished. And you can see that it doesn't matter what you study in terms of, if you're an engineer, you'll find a way, as long as you're happy and you love it. So let's start with my story. I was always a bit different, and you'll see in my career everything that Prof. Holm explained that engineers in the different schools do. I think I've done almost all of it because I love trying new things. And you'll see in the world there is a lot of place and a lot of opportunity where you can try new things also. People are very open to it, especially if you're an engineer and you come to solve problems for them. So when I started my journey as a child, I think most of you don't know what to study. And I didn't know what to study. The problem is, usually when you're ready to be an engineer, smart, you're very good at most of the subjects that you can do. And that's really where the theme of this comes in. You have to be brave, because now you have to make a really big decision in your life and you don't know what to choose. So in my case, I was very good at all my subjects except biology. So those of you who are good at biology, you're a step ahead of me. But I actually couldn't decide, so I took a gap year. So those of you who can't decide will hear my whole story, and it ended well for me, because the truth is, whatever you choose within engineering, you'll make it work, because it's a really wonderful field to be in. And if you have a passion for it, especially electrical or mechatronic engineering, you'll really love it. Lieta, do you want us to answer as we go, or?
Continue with your story. I'm just posting them as they come so that I don't.
Okay. So yeah, like I said, I took a gap year. I couldn't decide, but I did know I was coming back and I was going to do engineering. And the reason I eventually chose engineering, yes, I was good in all of my subjects. I was good at math, I was good at physics, I was good at economics, I was good at accounting, and it opened up such a world for me. But it came down to, I had a conversation with the psychology. One of our teachers gave us some advice, and it came down to the following. I wanted to build robot arms, which is something I think Lienza has built. I haven't built it to date. It turns out I'm not good at that stuff, although I still love it. And as a child, my mom will tell you, I took everything apart that you can imagine. I wanted to know, how does toothpaste work? How does the ATM work? And that is typical of an engineer. You want to know how things work, how can you make it better, and how can you work with people? Why is it doing what it's doing? And in that, what is usually you can't get it back together. But that is luckily your parents' problem mostly. Okay, and then I found my way to the Northwest University. So obviously I would recommend that you go and study there, but the reason I chose it was, if you don't know, it's a very tight community. It's very nice. Lived in the hostel. There's hostels where you can live on your own in a room, or you can share in a room. It's a really nice community to live in. And for me as an engineering student, I needed that, because I came from a year where I was on my own, was very independent, and then I needed something where I could grow as a person, and the Northwest University provided that for me at the time. And then you'll also see years later in my journey, I did a master's in engineering management. I did not do it directly after I studied, like most people do. So I first went to work a bit, find out what I love, what I'm good at, and it turned out that maintenance was in fact something that I love, and the master's in engineering management offered that for me. And then also I'm a professionally registered engineer. I think all the engineers here today is. And when you're an engineer, there's a body where we all partake in it. And it's really nice. It's a place where you can and just register yourself as a good engineer to show that you follow processes as a civil servant in South Africa. You do the right thing, you do good quality work. I'm going to sell EXA now, but we'll have that discussion a bit later. So like I said, that's how it all started for me. And then I was very blessed to get a bursary at Sasol. So those of you who want bursaries, you'll hear a bit later, I actually worked in the Sasol GDP program, and I'll give you some tips there that I hope will help you. But I would really like to encourage you, if you apply for bursaries in your matric year and you don't get a bursary, please don't give up. Apply again in your first year, apply again in your second year. Because these bursary programs, there's always spots that open up. And in my case, in my final year. So please don't give up. If you don't get it in your matric year, please continue with your studies. Please go on. When you study at a good university, it will all fall in place for you. Okay, so I started, to explain to you guys, I started as a control system engineer, and this is how things talk to each other. Then I had the opportunity there to work in projects, to work in maintenance. We replace things, we build new things. And after that, I realized that I actually love maintenance and I want to try that. And then I got involved with how you maintain these systems. And those of you who think about the future, small things are being introduced now, like how do you look at drones? And this is typically where engineers like us come in. We need to see, what do you do with the data? Because you can't just have a drone flying around and you do nothing with what it's seeing. And then after that, I went to go to the graduate development program. And the reason we mentioned this specifically is so a graduate development program is specifically a program that takes you from a graduate until you're appointed in an engineering one, or whatever the entry-level position in that company is for engineering. And they typically teach you company-specific things that you need to know. And it really differs. The banks have it, we at Sasol have it, and we're very proud of these programs because you're really one of us. We want to teach you how to be a good engineer, how to do things the right way. And it's designed to answer those questions that you don't know you need. Typical things will include, what are the standards that you should be using? Let's say we are importing something from America that was built here. are you allowed to use it in South Africa? That is a typical standards question. How do we do projects? Who do you have to ask for money? The specific processes that you have to follow. And this is what a graduate development program offers you. Provide a safe space where we teach you what you need to know. You don't know what you don't know, but we'll tell you what you need to know. And after that, we'll point you, will be a great engineer. And then I think that will also come into mentoring. So mentoring is a big thing. You'll see when you start working, I would highly recommend, if you forget everything today, this crazy lady telling you stuff, please remember the mentor is very important. It will really make, I won't say it will break. If you don't have a mentor, you will not be unsuccessful, but it really makes a difference. So if you ever have the opportunity to get a mentor, I highly encourage you to take it and that you ask relevant questions. I know Leonta provides a space where you also get mentoring. So after that, I joined the IoT, the big data, like Prof explained to us earlier, and now the world is open to just a significant way. And what does that mean? As an engineer, I can literally help any function in my company. So the thing with electronic is we work in teams a lot. We work with mechanical engineers, we work with electrical engineers because we love to automate and help them. And now I do projects for supply chain where we take them, help them make decisions, for finance, for CAs, where we show them where's opportunities to make money. Who else? We've helped our shipping team to see where's the ships in the country and how can they see where problems might arise. So as an engineer, if you can't choose, I would urge you just to know that the world is your oyster. There's so many problems to solve. It is really never boring. If you were like me, I can't design things, I'm not smart enough. Although I was top 10 in my school, and everyone tells me you are smart, you can do this thing, but in your heart, I don't fit the mold of someone sitting there. If that is the mold you have, that really is not what it is. Engineers are team players who help people to solve problems. And like they say, we don't just help companies, we help everyone. And we solve social problems, we solve financial problems. And that's what makes engineering so wonderful, because it just really, there is no limit. During a journey of being an engineer, you will however find some challenges. And I think that's the nice thing of communities that's also set. So if you read my bio, one of the things I'm very involved in a nonprofit, which is the SRC. So if you decide to become an engineer, if you're a doctor, a nurse, anything, there's always these fraternities you can join. And there you might not be a leader in your company, but you have an opportunity to always be a leader in industry. You always have a say. So there's always these fraternities where you can join. You can meet peers. You share the same interests that you do. There's always events. So we always, we joke golf days. Golf days is fun if you like golf. If you don't like golf, in our fraternity, we typically have a high tea where we offer females networking opportunities. So I know when I was young, everyone told me, there's not a lot of females who won't like it. For me personally, it's not true. I love it because my peers are like-minded people. We all want to solve problems in an efficient way, and we want to help people. And helping someone at work is still helping someone. And a lot of people miss that because there's not a lot of careers where you can really be happy every day that you did something that changed the world for someone. And engineering is really one of those roles. To conclude, the graduate development program that I worked in, so I always talk about it because there's a lot of small things that people don't know. Like I said, please, if you have a bursary, make sure you apply every year, not just your final year. Vacation work, those of you who get the opportunity to do vacation work, please take it. That's a lot of times where companies see you and then they give you an opportunity when you apply later on. if you ever get the opportunity, please take it to do vacation year. And then also, if you do enter into a graduate development program, make sure you make the most of it. But it's a difficult time in your life because you'll see that as soon as you have studied, you just want to go out and change the world. And you sort of get into this program where they want to teach you other things and you feel you're not changing the world. If you ever think about it, or come back to this chat and contact me and say, I'm in this graduate development program and I need help. But really, if you're currently studying, please start looking out for these programs. All of the companies have them. It's not just for engineers. At Sasol, I think we do lawyers, CAs, engineers, these different ones. And please, whatever you decide to study, find these programs because it's really just a safe community where a company helps you to be the best you can be. And I also want to say the flip side on that. If you do not get into a GDP, please do not feel that you are a failure. There's a lot of people who never entered a GDP and they are extremely successful and they change society every single day. So please don't make me sound like this is the only thing you have to do. And then also just something to remember, those of you who are still studying, you have up to 3 years to apply for this program. So please, if the year when you finished your studies and you can't get into a program like this, please continue to apply for 3 years after that because you're still eligible. That's my story, Lenta. I'm not sure if there's any questions. It's a bit strange. I see a lot of questions popped up.
Yeah, I see there's one question asking whether or not it is important or advantageous to have a background in coding or programming if you go into computer engineering. I can maybe answer that one because I was definitely not the best programmer far into my career. So I didn't take it as a subject at school. I managed to pass some of the coding subjects even in the first 3 years. And it was even only in my final year when I really needed to apply it for my project that I really learned one big lesson that in the Moderatiegheidsche competition I really tried to teach to all of you, that you are just supposed to think about this problem the way you would think about any problem and use programming language then as the tool to solve that problem. So as soon as you see, it's similar to the physics and chemistry debate we had yesterday. Just like in physics, you use math as a tool to solve some physical world problems, or you use it as a tool to solve some chemical equation problems. Programming is just another language we use to tell a computer how to do certain things. So as soon as you really understand what you want a computer to do, then you understand what to tell it and how to use specific instructions to do that. So I wish I knew that earlier, and that's why I was really glad when I was moved to that second year subject and I got to teach that to a lot of people. It felt like giving them superpowers, but it's definitely not something that you need before coming to study. It is not something that you need to be specifically good at. We will teach you while you're here, so you don't need specific subjects apart from mathematics and natural sciences. And then or physical sciences, I'm not entirely sure what they call it at school these days, but those two subjects. And then language. I can't emphasize enough that I remember being at school and all the boys who was going to become engineers told my language teachers that they don't need to be good at language because they are becoming engineers and they will not need languages. And I loved languages, so it was never something that I said, but I frequently heard that, and it actually made the language teachers very angry when they heard stuff like that. And what happened in the end is that once they got to studying, they realized that unless you have documented something and unless you've written a report about it, it didn't exist or it didn't happen. So that's why language, a mark of 60 for the language of instruction, is so important for engineering, is because communication is a huge part of what we do. And I think Prof. Willem and Anna-Marie will be able to back me on this one, is you can't undersell how important it is to really tell someone exactly what you mean and what you want them to do specifically. Because if you give bad instructions, then you get a bad outcome, or you get an outcome that's not aligned with what you actually hoped to get. And specifically because engineers, a lot of the time we do the design and we do not necessarily do the implementation. They will be just like chemists will do the testing for chemical engineers, technicians or programmers will do the implementation for us. So in your undergraduate degree, you will get the tools and you will know how to do it, but it is not necessarily true that you will be the ones doing the implementation. In MediHive, my company, for instance, where we develop medical devices and specifically digital health solutions, I am the one focusing on the user experience design, the look and feel, the logical flows and the user stories of a specific software product, but I'm not the one implementing it because I'm too slow. So I pay a programmer to do that for me because he is not trained, and that's one of the big questions we often get asked. What's the difference between computer science and computer engineering? Computer science students get taught to program really well and to do use many different languages and to use a lot of different tools. We get taught how to think about a problem, how to break it up into a lot of smaller parts. This is actually something that I learned from Prof. Willem, since he taught us systems engineering. So how to deconstruct that problem into a number of smaller parts that we can actually then address separately, and to evaluate the best solution for each one of those smaller parts. And then we write a specification, and that specification gets passed to someone who then actually do the implementation. So sometimes it's us and sometimes it's not us. It depends on the team you're in, and it depends on how much time you have or how much money you have to have a solution implemented. But I think there's a lot of misconceptions about, a lot of careers actually, but definitely that about engineers and specifically what we do and how we do it. So that is one question. Then is computer applications technology important for computer engineering? Again, I just answered that one. That's what the rekenaar study is called these days. Okay. Then how far are we with developing robotics? That will depend on what you mean by how far we are with developing robotics. We've been using robots for very long to do various different things in the world. If you mean robots like robots that can walk, who can walk around, and so like bipedal robots that look like humans, there's amazing developments happening all over the world, and I can share some of the links with you. But that's not the only robots that exist. I don't think there's a single car being manufactured without a robot doing a lot of the assembly. There's this phone of yours. This was definitely assembled by a robot, because if you were to open it and to see the microelectronics inside there, it's definitely not something you can do by hand. Maybe Prof. Willem, can you assemble such small things, since you're a pure electronic engineer?
Are you putting me on the spot, Prof. Leonta? I think what we have to understand is that, and it's very interesting, that the latest development in robots have been on the artificial intelligence side of it. And it's really machine learning, in other words. So that's where the focus is. And some of the computational abilities in the past have not been high enough to support the implementation of higher level thought and control processes in smaller robots. But nowadays they've become so powerful. You can imagine, and I can't even remember. I think it was one of the first cell phones that came out that had enough processing power to launch the rocket to the moon. And that was initially done by a computer that occupied a whole room. So you can imagine how that with Moore's law, it says that basically every, how many years, Leonta, is that? Every so often years, we double up on processing power. Is that right? I can't remember how many years that is, Moore's law, but you can
double check that for you.
But you can look it up. So the thing is that the processing power becomes more and more, and the amount of energy consumed becomes less and less. And you know the old Bitcoin thing. Remember, the amount of energy consumed by Bitcoin just to generate Bitcoins is humongous, and all those computers are running parallel. But when you build a robot, you don't have all that power. You can't plug it in. You have to have a battery or something that powers it up. So the one thing that limits us, we've used to limit us, was the computing power, and the other one was the availability of energy. But nowadays we've got lots of energy in small packages, and I think over the next 10 to 50 years, energy storage and the size of energy storage is going to be one of the biggest developments in the world, and that is what we have to look out for. So once that becomes small, and so small that we can power a robot, then we've actually come far with the development of robotics. There's a lot of fights about how we apply artificial intelligence and whether we should apply artificial intelligence, in the way it is being applied now, by spying on people and studying people's behaviors and so on without them knowing. And you might know about Mark Zuckerberg and Elon Musk and the guys having a big fight over in America on this topic. But indeed, we've come far, and lots of robots exist that can actually interact with humans in a way that you won't be able to almost see that it's actually a robot. So yes, emotions, the expression of emotions is the latest development in actual human-like robots, or the bipedal type robots that we talk about.
Yes, and another place where we actually also apply the robotics and a lot of aspects that are that come from that discipline is in prosthetics. And our faculty have made the decision, and our university have given the funding for us to compete in the 2024 Sabathlon competition. So that's the Bionic Olympics. I will always also post a link to that for you in the WhatsApp group. So that is where it's like the Olympic Games. We've all now been very active in that or monitoring that. But for someone with a disability, it is not necessarily easy to do the things that you take for granted. Something like breaking an egg, for instance, or crawling underneath a table to withdraw something. So the events in the Bionic Olympics is not about being the fastest or the best at swimming or whatever. It is developing the best engineering solutions that will enable people to do everyday tasks. So we will be competing in 3 different categories. You will always also watch a video after we log off Zoom. We will continue on YouTube channel where Ian will show you how to write your own little computer game, and it's really easy, and it's a very nice concept that was developed at MIT, and a programming language specifically for kids to start learning programming without feeling intimidated. So and Ian is an amputee himself. He lost his leg 10 years ago, and that's why it's so amazing to work with this solution on this solution with him, because I've always been someone that is really interested in understanding the problem and understanding how we can develop some solutions. But something that he said to me quite early on last year, and then we learned about the sabathlon competition and learned that is exactly why they started this whole initiative, is that a lot of the time, engineers think that we understand what the problem is and that the user should adapt. So if we develop some software and you can't use it, then it's you who lacks skills. We need to train you. And Ian then told me that as an amputee and someone who uses a prosthetic, he was frequently agitated by the fact that engineers would try to convince him why he is using the leg wrong, and he's the one that's not doing it properly, and not necessarily that they should rethink about how they develop the technology. So I think that's also something that's quite new these days, is that engineers are starting to rethink the way we approach problems and to make it much more user-centric. So I'm very excited about that. So that is actually somewhere where we apply robotics. Then if you're in high school doing physics, maths, and computer applications technology, does computer application technology advance you into computer applications? Yeah, sure. It's never bad to have it, but it's not necessary to have it. Then is machine learning a postgraduate facet of computer engineering, or is that more of more computer science? I think Perfolum, you typed an answer there, but can you maybe do it verbally as well, because our viewers on YouTube won't be able to see the chat.
Yes, by all means. So in order to do artificial intelligence, you need to understand statistics, you need to understand mathematics, and specifically mathematical optimization. You will need a foundation in pattern recognition. So all these require the basic knowledge. You get typically up to a third year in computer science or a fourth year in engineering, because we do other things as well, not only statistics and maths. And you need sound computational skills. So in other words, you need to be able to program. Now, there are advanced tools such as the Google tools and IBM and lots of the larger companies have started making available AI tools where you can program your own AI environment, looking at patterns, for example, trying to recognize patterns or identify anomalies and so on. But the challenge with that is if you don't have the underlying skills, you will never know what you don't know. You won't know if you make a mistake, and you won't know if the answer that you get is a general answer. It's only typically an answer to a specific question. Whereas with AI, you would like to apply the principle of generalization. In other words, when I do something, I need to be able to apply it over a wide range of problems and could be, for example, I might be doing facial recognition, and I might only look at one portion of a demography, and then it won't be applied to the rest of a population. So it depends on a whole number of things, but having the sound skills is a definite plus. So typically, you would be able to learn that in computer science and computer engineering, whereas with computer engineering, you will be able to solve a broader range of problems. And computer science, you'll be mostly bound to the software side of AI. I think it's a fair answer to that question, I think.
Cool. Okay, and then there's a question whether there's a difference between computer applications technology and IT. I think you're referring to undergraduate or to high school subjects. As far as I know, it's just two different ways of referring to the same subject. I will double check since I haven't been to school in 20 years, but I will investigate and come back to you on that one. I'm not entirely sure. Okay, then we have a question. I'm doing a chemical engineering second year at the NWU. How can this session help me to be the best chemical engineer? Well, I think it can help you to understand what computer engineers do and how we will make your life easier one day by helping you generate data that you can use to improve your process. But if you want to specifically have information on chemical engineering, then I suggest you watch the video that we shared yesterday, where Joni and Corneels shared their journeys that they followed in chemical engineering, both at Sasol and at Anglo, and they also shared a lot about the lessons they've learned along the way. So for chemical engineering, I really suggest that you look at that one. Okay, I don't see any other questions now. So I think that brings us to the end of this session. Any closing remarks from you, both Johan and Anneman?
Yes, it's a pleasure to be part of this. Thank you very much for the opportunity to both influence and be part of the development of these brilliant young minds. We hope to see lots of you in our school, but it doesn't really matter if you in our school or if you're doing whatever engineering, as long as you do engineering, we'll be happy.
Anne-Marie?
Yeah, from my side, also looking forward to welcoming you all into the community once you're all engineers or whatever you choose to be, and looking forward to the difference that we'll be making to the world.
Okay, so thank you so much for your time this afternoon, everyone. I really feel privileged to have this opportunity to speak to you every day. And before this for 2 weeks with Moriagatsi. So I think I've had my share of sharing my personal space after these 3 weeks, but I really hope that you learn something in the process. And yeah, even if you do not go into engineering like Prof. Johan said, if you're at least going into life, knowing what engineers do, you maybe will appreciate the technology that you use better or more. If you go into finance and you need to make the financial decisions on the stuff that we want to buy, I hope that you'll understand what goes into developing a product or developing a process, that you'll make those decisions more wisely. If you go into law, I hope you can defend us better because you understand us better. So it really doesn't matter what you end up doing. But I think what really matters is that we actually appreciate our differences, and that we appreciate that there's no easy degree to study. There's no easy jobs out there. Everything takes aptitude and everything takes effort. And if it's worthwhile, you will stick with it. And I really think that whatever you do, as long as you don't think you're better than anyone else, you will be a wiser and a great worker, and it will be someone that means something for your organization. So with that being said, we're going to log off the Zoom now, and then we will move to the live stream on YouTube. I really hope that you registered with with an account, a Scratch account. If you haven't done so, just pause the video and quickly do that. I think actually Ian will take you through that as well. But I hope that this will just be something that stimulates interest with you and shows you that programming is really easy once you actually just realize that it's just logical steps. And then I hope that today will not be the only day that you play with that platform. I was exposed to it when I took the Moriagatsi winners to San Francisco 2 years ago. And I took them to the Computer History Museum in San Francisco. And there we played with this specific technology. And since then, I've showed it to my 9-year-old and my 6-year-old sons. And both of them enjoyed it immensely, and they are now writing computer programs. So if the two of them can do it and they can barely read, I'm very much sure that all of you can do it. So take it on with the confidence that a 6-year-old, only a 6-year-old can do, that believes he can change the world and he can do anything he puts his mind to. So have a good evening, or a great afternoon, and I'll see you again tomorrow afternoon when we join with the industrial engineers. Goodbye.
Hi everyone, welcome to Programming Scratch. Today I'm going to teach you how to make your very own game. Here's a preview of what your game will look like once you've finished. Before you can get started, you need to open Scratch on your internet browser. I'll show you step-by-step instructions on how to do this. First, start by opening your internet browser. Search for Scratch. Open the first link that pops up. Now you want to join Scratch. Click on the Join Scratch icon on the top right of your screen. Follow the steps to join Scratch. I've already joined Scratch, so I'm going to sign in. Once you've joined Scratch and signed in, click on the Create button on the top left of your screen. Next, let's move over to step 2. This will be a short overview of Scratch. Scratch uses a functional block programming language, where each block represents a certain function. In Scratch, you can select different backgrounds for your program. You can select sprites, which are random objects to insert into your program. For example, the cat. Scratch also allows us to change the costume of certain sprites. Some sprites have more than one costume. If you click on the next costume, it'll change what the sprite looks like. Another thing Scratch can do is to insert sounds into your program. If you'd like to insert a sound, you can click on the left bottom button, and there will be various different sounds you can choose from. For instance, you can go to animals and you can have a chirp sound play. In step 3, I'm going to show you how to add a background and add sprites to your program. Let's go back to the code. You can do this by pressing the button on the left top of your screen. Okay, the first thing we're going to do is add a background. Well, let's just delete this cat sprite first. You can click on the right top of this icon, you can click delete. Okay, so let's add the background. I am going to choose the Night City background. Next, we can add a sprite. You can choose any sprite you want. I prefer to use, where's Dot? Dot the space puppy, because he has a nice walking animation. Okay, let's change the size of Dot. So you can click on Dot, and here you can change the size of him. Let's make the size 50. There we go, and let's line him up nicely with the road. Okay, next let's add a ghost. Let's find the ghost. There we go, there's a ghost. Let's also make the ghost a size of 50. There we go. Okay, so now you can change the ghost color if you would like. You can click on this full button here, and you can click on the ghost. Let's make the ghost, how about pink? Pink's girly. Girls are scary, especially when they become your wife. There we go. Make sure you do this for each of the costumes. There we go. Okay, now I'd like to change the direction of the ghost because he's going the wrong way. So make sure when you click on the costume, click on this bottom costume, the ghost D, and then you're going to go to, make sure your ghost is selected, and then we're going to say direction, and then we'd like to turn the ghost around. Okay, but now he's upside down, so let's just switch him around like that. There we go. And there you have added all your sprites and backgrounds. In step 4, we're going to make dot walk. Okay, so let's go back to the code. We are going to start by clicking on dot. That means we are going to start programming with dot. To start off, we're going to go and click on events on the left of your screen, the yellow. And then we're going to use this when green flag is clicked. This means when this green flag here is clicked, something will happen. Okay, now we want to fix Spot to this location he is in now. So if you click on motion, the blue one, and then you'll see we're going to say go to. You'll see there's X and Y coordinates. If you look on Spot, this is the same coordinates he is in this current in the current place he is in now. Okay, so that's where we want him to be. We want him to stay there. Okay, and then we want Spot to walk. So we're going to go click on Control, the orange button. We're going to say forever. This is a loop. This means whatever is placed inside here will keep happening forever. Okay, so now we want Spot to change his costumes as he's walking. So if you look at costumes, you'll see if he changes through these costumes, it'll look like he's walking. We do not want him to look back, obviously, because that's not going to be walking. Okay, he has to look forward where the ghosts are. Okay, so we're going to delete this one. Okay, go back to your code. So we're going to say, go to looks, the purple, and you're going to say next costume. So he's just going to keep on changing costumes. And then we want to put a little bit of a delay in. So we want to go to a costume, wait a bit, and then go to the next costume. Otherwise, they're going to switch too fast. So we're going to look for the wait function. There it is, wait. Wait 1 second. That's a bit fast, slow. So let's make it 0.1 seconds. That'll make it look like he's walking quite fast. Okay, so now when I click on this green button, the go flag, there we go, there, Spot's walking. In step 5, I'll show you how to make dot jump. We want to make Spot jump as the space key is pressed. So we're going to go to events, you're going to click on the when space key pressed block and drag it in. You can put the block wherever you want. Okay, so as the space key is pressed, whatever goes on beneath it will happen. Okay, so let's make dot make a sound when he jumps, or when space key is pressed. So you're going to go to sounds, you're going to go to choose a sound, and then you're going to go to animals. So let's make him bark. There should be a bark or dog there. You click on bark, or let's take that one, he's a little dog. You're going to click on it, and then you'll see it has been added. So you go back to code, And then when space key is pressed, you go to sound, you say start sound dog 2, which is the bark. So now when I press this button and I press space, he will bark. Next thing we're going to do is we're going to make him jump. So we're going to go to motion on the blue, and then we're going to use the glide function. This one. Okay. So Dot is going to glide up to a position. He's going to go from one position to another position in 1 second. So this means he's currently at this position. We want him to be a bit higher, so when he jumps, so let's move him. He should be a bit higher than the ghost, eh? There we go. And you'll see his dimensions. It's going to be Y must be moved to 11. Okay. So we're going to make Y 11. And then that only moves him to the top. We need to move him back down again. So we're going to use another glide function to move him back down. And then we're going to move him back down to his original position. So that would be, just, there we go. So it's minus 195 to minus 78. Now when I press the space button, he will go up and down, but that's a really slow jump. Let's make it a bit faster. Let's make him jump in 0.4 seconds. Let's go up and 0.4 to go down. So if we press it again and we press space, there we go, that's a bit faster. And there we made Dot jump. In step 6, I'm going to show you how to make the ghost move. To make the ghost move, we're going to first start by clicking on the ghost sprite. Now we're going to start programming on the ghost. Okay, so let's start with a control, or event, sorry. So when the green flag is clicked, we want to hide the ghost. We do not want to see the ghost. So as the green flag is clicked, that hides the ghost. Okay, now we want the ghost to keep on coming. So let's go to control, and then we want to repeat it. So let's say we want the ghost to appear 5 times. Okay, now we are going to go to looks. We're going to switch the costume a bit. So this means that every time the ghost comes past, a random costume will be chosen. So if we can look at costumes there. So any of these 4 costumes would randomly appear as they pass by. So we're going to say switch costume to, and then we're going to go to operators. And this picks a random value. So pick random. There is only 4 costumes, so you're going to say 1 to 4. So any of those 4 costumes will appear randomly going past Dot. Now we want to initiate the begin coordinates of the ghost. Okay, I'm just going to make the ghost appear again. So if we look, we want him around there. So let's say about 250 to minus 92. So we're going to say motion, and we're going to give him a fixed position. So we're going to say go to. Let's make it 250 and minus 92. Okay, so that's going to give him a fixed position there. Now we want the ghost to appear. So let's say show ghost. So now the ghost will appear. Next, we want the ghost to glide from the right side to the left side of the screen. So we're going to go to motion, and then we're going to say glide. No, not that one. Glide. There we go. We want that one. So in 1 second, he's going to glide from his position there to the other side of the screen. The other side of the screen would be minus 250 on the x coordinates. So if we click the play button, he will move from right to left, and it will be different costumes now and then. Okay, and it only happens 5 times. In step 7, we're going to make the game stop if dot touches a ghost. We're going to move back to programming dot now, and then we are going to add a broadcast. So you're going to add broadcast, and then you're going to give it a name. So new message, and say start, meaning the game has started. This is going to broadcast out a signal. And then we're going to say, when I receive the message. So as this signal is received, it starts, moves to position, it sends out start. So as start is received, you are going to run a loop. So it's going to be a forever loop. It's going to keep on running. And then we're going to say, use an if function. So if something happens, then it's going to do something. Okay. So if the dot touches a ghost, it's going to do something. So if we're going to go to sensing, let me say touching. So there in touching, we're going to use if touching ghost, then something will happen. Now we want to say broadcast again. So we're going to go to broadcast, and then I wanted to broadcast that the game is over because you have lost. Game over. Okay, and then we want to stop the game, so we're going to go to control, and then we'll say stop all. Okay, so the game will stop as that happens. Okay, so when you press that, it touches, nothing happens anymore. That means the game has stopped. So each time it happens, the game will stop. So this means they are touching each other. Okay, next we're going to receive the broadcast. So when I receive game over, then something will happen. So let's make Spot say something when he comes in contact with a ghost. So let's say we're going to go to looks, and then you will say say. We want him to say something. So let's say ouch, because ghosts hurt dogs and doesn't pass through them for some reason, but that's what happens. So now when Spot comes in contact with the ghost, he's going to say ouch. Ouch. Okay, so if we keep on going and we try and jump over him, nothing will happen. Oh, except if we do that. But anyway, and there, that piece is done. So in step 8, I'm going to show you how to make a score. Okay, so to add your score, you are going to click on variables, and then we're going to make a variable. Let's call the variable score. Okay. Next, we're going to add an event. So when the green flag is clicked, the score will start. So we'll be able to start scoring. Okay. So then we're going to go to variables. We're going to set the score to 0, because when you start off you should have 0. Okay, so score to 0, and then we're going to repeat this 5 times. Seeing that the ghost is only going to appear 5 times, we're only going to have the score go up to 5. So we're going to go control repeat. Okay, so we're going to make that 5. And now we're going to wait 1 second for the ghost to pass, and then you'll have a score of 1. seeing that the ghost takes 1 second to move past. If you have one ghost that goes past, you have 1 score. If you have another ghost that passes, 2 scores. And then so on. So we're going to say wait 1 second. And then we have to, obviously, each time the ghost passes, you have to add 1 to the score. So it goes from 0 to 1 to 2 to 3 to 4 to 5. So we're going to go to variables, and then we're going to change score by 1. So it's going to add 1 each time it goes past. So when we click here, obviously you have 0 if you touch the ghost. So if you jump over it, you have 1. And if you can make it to the end, hopefully. There we go. Oh no, I touched it. And it goes up to 5. So at the end there, we managed to jump over, but the ghost and Dot is still touching. This means we have to move Dot up a little bit to the right, so they do not touch each other. So let's move him up to around, let's make it minus 170. So we're going to go to the x-axis here, say minus 170, and we're going to do this by each of the x-axes. Okay, if we run it now, and we make it through everything, oopsie. There we go, no longer touches, and we're all good. So in step 8, we're going to make the ghost dance in humiliation of our glorious victory. Let's first add a song to start as the game starts. So let's go to sound and add a song. Let's go to loops. Let's choose something spacey. Space, because Dot is a space puppy. No, that sucks. Let's go to loops. There we go. Let's go for that one. Okay. That's added. We go to code. Go to sound. We say play sound. And we say dance head, whatever it is. And then we start. Let's see. There we go. I have some beats while we're playing. Next, we're going to go to Ghost. And then we're going to make him dance. Let's start off by making a song play when we win. So let's go to sounds again. Choose a sound. Let's say reggae. There we go. We go to our code. And then we say, wait, let's make the ghost first move to the middle of the screen. Let's do that. Let's have him go around there. That's so we're going to say motion. We're going to say go to that position he is currently in. Now I want him to stand there. Now let's add the sound. So as he moves there, we'll start sound as we win. Now let's have him dance. So we're going to go to control. We'll have a repeating loop. So let's make it 5 and have him change to costumes to make him dance 5 times. So we're going to say looks. You'll choose next costume. And now as you win, he's just going to go looping through the costumes and it'll look like he's dancing. But again, like last time, we want to add a little delay there. So we're going to go to wait. And we will say wait 0.3 seconds and that will make him dance. Let's see. Whoopsie. There, now your ghost is dancing for you. Let's make the ghost say something to us. And let's choose the other costume. He has a nice costume. Let's make him look like that as he's speaking to us. Okay, so we're gonna make sure we choose that costume. So we're gonna say looks, switch to costume, and this one is costume C. So we're going to choose there, ghost C. And then we want to have the ghost say something. Let's have him say it for a long time. Let's see, let's say, I don't know, say whatever you want. You are awesome, or let's make it space puppy power. Oh, there we go. Let's make him say it for 7 seconds. And then after that's done, we want the whole program to stop. So we'll say stop all. How about we add some balloons while they do that? Let's go to choose a sprite. Let's say balloon. Let's take that one. Let's add, make it a little bit smaller, make it around, let's say 70. Let's add another one. Again, balloon. Make that one 72. There we go, there we have some balloons. Let's change the color of the balloons. Let's make one yellow. Let's make the other one purple. There we go. Now we want those balloons to appear as while he's dancing. So we're gonna say, we're gonna go back to the ghost. We want to send a broadcast out to say he's going to start dancing. Well, let's make it after he's danced. So let's say we want an event. We're going to broadcast, and let's make the broadcast, how about new message? Let's make the broadcast win. Okay, so win will be sent out as we win. Okay, so now we're going to go to balloon 1, and then we're going to say, as we receive the broadcast win, then do something. Okay, but at the moment the balloons are visible, so we'd actually like to hide it first. So let's say first when click, looks, and we want to hide it. Let's hide it away first, and then as we receive the broadcast win, we want it to appear, so show. So now it's going to show. We're going to have to do exactly the same for balloon 2. So events, when clicked, looks, you're going to hide it. And again, events, when you receive the broadcast win, then show it. There we go. Let's try it. Awesome. There we go. Make sure to change any of the colors you want, and you can even change dot. Make him something else. You can make him a unicorn if you want. Congratulations, you just programmed your own game in Scratch. I hope you all enjoyed it. Thank you very much.